Good evening. Am I audible? Will you please confirm me? Anyone, please? Can you reply? Am I audible? Okay, it's good. So I'll wait for 1 or 2 minutes. So let all of them join. Okay, I think we can start. They will be joining. Right? Okay, let us start our session. And today I said that I'll be discussing on the problems on control system. And this so let me first discuss basic concept of stability. Then we'll come to the problem session. Very briefly I'll discuss. Okay, I think it is visible. Everything is visible. Okay. So in control system, what we find, first we should have one system or plant. That function will call it G of S, and here we can have some feedback mechanism. That function will call it H of S. Generally we will consider negative feedback. So this reference input R of S, all are in Laplace domain, that you understand. It is fed back here. This is plus, this is minus, and then it is connected to the plant G of S. Right? So this is the negative feedback, and this is called controlled output CS. So we have transfer function, closed loop transfer function CS upon RS is simply GS upon 1 plus GS HS. Right? Am I clear? This part? Okay. Right? So this transfer function G of S, now here the stability depends on this factor, this denominator factor, 1 plus GSHS. So this 1 plus GSHS and its roots, we will find out this equation, and that is called characteristics equation. That you understand? Then solution of this one will give you closed loop pole, and the system stability depends on the closed loop poles only. Okay, and what is the condition? Very briefly I am discussing. I am not discussing the theory. I think theory is known to you. If not known to you, please let me know. I will make some video later on. So first you will draw the S-plane closed loop poles. If all the poles are lying on left hand side of S-plane, this is the real axis and this is your imaginary axis. And this left hand side, if poles are there, then only it is stable. If we find any pole on right hand side, it is unstable. Right? So this is the situation, and if any pole is there on the imaginary axis, suppose I have one pole here or here, that time we will call it marginal stability or critical stable system. Critically stable or conditionally stable or marginally stable. The same meaning is there. So if roots are on the imaginary axis. So this is the concept. Now we will work on this concept only. We will try to find out the roots of the closed loop system. If all the roots are on left hand side, it is perfectly stable. If we find at least one pole on right hand side, it is unstable. And if we can find poles on imaginary axis, it is called marginally stable or critically stable, okay, or conditionally stable. Is it right? Now it should not have any multiple poles on imaginary axis, then it will become unstable. That also it should take care. You should not have multiple number of poles. Is it okay? Now we can consider the examples we will consider later on, and then we will consider Routh-Hurwitz criteria. So you can see that this 1 plus GSHS, and that is equals to 0, and this equation we need to solve, and its solution should be on the left hand side of S plane, then only it will be stable system. Otherwise you will get unstable system. So how to get this idea from Routh-Hurwitz table? I will take one example, then I explain quickly, because I hope you have certain idea on Routh-Hurwitz table. I will be discussing some problems on this topic, okay, later. So for one example I will consider. Suppose GSHS is 10 upon S into S plus 1 into S plus 2, right? Now this GSHS, now for this one I will get one characteristic equation like that, 1 plus 10 upon S into S plus 1 into S plus 2, that is equals to 0. So if we simplify it, what we will get? S into S plus 1 and S plus 2 plus 10, and that is equals to 0, right? So from here, now first what we will do, we will expand this term. So how to expand? So S is there. First I will multiply first letter 2, S square plus 3S plus 2. Then I will add 10 and it will give you 0. Right? So here you will see that it is S cube plus 3S square plus 2S plus 10, that is equals to 0. So this is your characteristic equation, and now from here one minute. So this equation we have got the SQ plus 3s square plus 2s, and then we have got plus 10 equals to 0. Then what we will do, we will try to make Routh-Hurwitz table. So this is 2, then s to the power 1, s to the power 0. So this table we have to make. So how to make this first row? So SQ means this odd powers, SQ s to the power 1. So its coefficient I will collect. This is 1, this is 2. Then s square means even powers. Its coefficient is 3, this one, and then it is 10. Right? Then next one will compute s to the power 1, this coefficient. So what I will do, I will multiply this 2 first. So 3 into 2. Then I will multiply next to this 2, 1 and 10. So minus 1 into 10 by this element 3 that is divided. Okay, and this is not there, so s to the power 0 will be the last one, this 10 that is coming here. So this value we can compute. So 6 minus 10 is minus 4 upon 3. Now we need to check the first column of this Routh-Hurwitz table, and if you find all the elements are having same sign, then there is no pole on right hand side of S-plane. But if there is any sign change, that number of sign change will give you number of poles on the right hand side. So here you can note that first one is positive, second one is positive, and third one is negative, and last one is again positive. So here there is a sign change from second row to third row. Again this negative to positive, another sign change. So I have two sign changes that imply two poles on right hand side of S-plane. Okay, this is the conclusion. So if I have said that if we find any pole on right hand side of S-plane, the system will become unstable. So for this kind of characteristic equation, the system is unstable. Clearly we can see. So this kind of problem we will be discussing in this video. We will discuss more than 7 or 8 problems. So take care of these things. So if you have any doubt, please let me know. Okay. So are you ready to go through the problems? Please reply. Do you need more idea about this stable condition for stability or Routh-Hurwitz criteria? Anybody? Okay, so I think we can start. We can start then. So if it is everything is fine. So first problem we'll discuss this one. So you can read this one. I think it will be better if we. Now this is the problem. I think the screen is visible now. Now here we have one system. The forward gain is G of S, that is given 1 upon S plus 1 times S plus 2 times S plus 3, and K is given. K is proportional controller, you can say, the gain of this proportionate controller K. Now question, it is given that we need to find out the positive value of K for which the gain margin of the loop is exactly 0 dB and phase margin of the loop is also exactly 0 degree. Okay, try to understand what is the meaning of this, right? So it says that the gain margin is 0 dB. There is no margin. Margin is 0. Again, phase margin is also 0. Means it is under critical condition. Means conditional stability. In other words, I can say the closed loop poles are on imaginary axis. Is it clear? Can I make this conclusion? That once there is no margin, gain margin 0, phase margin 0, that implies that it is under critical condition, it is on the verge of instability. We can say it is on conditional stability. Right? So this is the problem. We need to find out that K value for which it will be on that critical condition. Okay, so how to find? So I'll consider these things, this size. And this problem appeared in GATE ECE 2016 problem. Now how to solve it? Okay, so let me consider this one. So we have characteristic equation there like this, 1 plus K times GS, there is no HS, HS is 1, so that I can put it equals to 0. Is it okay? Now we will replace 1 plus K and GS is replaced by this one, S plus 1, S plus 2 and S plus 3. Okay. Then that will I will put it equal to 0. Now can you find that solution for which anyone please can you answer this thing? What is the value of K for which it will be under critical condition? Anybody? Do you have any idea how to proceed this thing, how to get this K value? So what I will do, first I will consider this characteristic equation, S plus 1 times S plus 2 times S plus 3 plus K, and that is equals to 0. You can expand easily. So what you will do, so first I will consider letter 2. So this product will give you a square plus 5s plus 6 plus K equals to 0. Okay. If I make any mistake, yes, poles should be on left hand side. So you can understand that this system is having 3 poles. Okay, third order equation is there. So equation, some pole could be on left hand side, but if I find at least one pair, conjugate pair on imaginary axis, then it will be on the verge of instability. Or if I find one pole at origin, then also it will be unstable. So not unstable, critically stable. Right? So this is the condition. So some pole could be on left hand side, but at least one pole on the imaginary axis, but there should not be multiple poles at the same place on imaginary axis, then it will become unstable. That you understand? So here we need to find out the K value for which it will be under critical conditions, the marginal stability. That is the concern. So for that I want to use Routh-Hurwitz criteria. So first I want to get total characteristic equation, the expansion of this one. So that's how I will do these things. So I will multiply again S plus 1 with this one. What I will get? So S into S square is S cube. Then 5S square plus 6S square. It will become, so this will be S square plus 5S square. It's 6S square. Then 5S plus 6S, 11S plus 6 plus K equals to 0. Is it perfect? Right. Now you can see the answer. What is the answer? That I will proceed these things. So you see the answer is 60. Now we will work on that. So already we have got this equation. So equation is SQ plus how much it is 6S square plus 11S plus this your 6 plus K. This is your 6 plus K, that is equals to 0. So can you make Routh-Hurwitz table? So SQ, S square, S1 and S0. Okay, I hope you can do these things. So what is the SQ? This coefficient is 1, this coefficient is 11, the next S squared coefficient is 6, then constant term is 6 plus K. Now I can find out the coefficient of S to the power 1, right? So how to find these things? So this 1 into 6 plus K, so first I will multiply these two. So 66 minus this one 6 minus K upon 6. Okay, and then nothing is there, and last one should be 6 plus K. Am I correct? Is it clear to everybody? Okay, right? So now what I'll do? I need to get marginal stability, and for that I need to get some poles on the imaginary axis, and this is possible if we can consider this second one. Okay, I can have something like that, but if this term is becoming 0, then I will get one auxiliary equation in the above. Okay, so first I want to make this thing equal to 0. So what is this? So this is your 60 minus K by 6, that is equals to 0. That implies K equals to 60, right? So if K equals to 60, then this element S to the power 1, this value is becoming 0, and it implies that the above one will be one auxiliary equation. What is that? It is your 6 S square plus 6 plus K, and that is equals to 0. So this implies, you can see, if I replace K equal to 60, then 6 S square plus 66 equals to 0. So from here I can take common 6 S square plus 11 equals to 0. So that solution is S equals to plus minus square root 11, but one J will be coming because minus square root 11. So I will have one J square root 11, one is minus J square root 11. Okay, so what are the easy things that you should do? You should make one element of the first column that you have to make it 0. If you can make it 0, the above row will give you one auxiliary equation. Preferably the power is even, the S square or S4, that kind of things. Then you will get one equation, auxiliary equation, and from that auxiliary equation we can find out the roots, that is the real roots, means poles of this closed loop function, and you will see that poles will be on imaginary axis because it is a square plus constant, some constant. It is always on the imaginary axis. That's how I am saying that try to make this S to the power 1, this coefficient equals to 0, that is the idea, and from that you will get the value for K. So here K is 60. Any doubt please? Anybody? Please let me know if you have a doubt, or you can say it is perfect, there is no doubt. Then I will go to, yeah. So one is replied, Joy. So others are fine. Okay, let me go to the next problem. The second problem, the transfer function of a linear time invariant system is given by this thing, h of s. This is the transfer function they are saying. Okay, that means there is no poles, only zeros. Only h of s it is given. So h of s is 2 into s to the power 4 minus 5s cube plus 5s minus 2. This is the transfer function, and now we need to find out number of zeros in the right half of S plane. Okay, so how to find number of zeros on right hand side of S plane? Again we can use Routh-Hurwitz criteria. Okay, so what I will do, we will consider this h of s, right? So this is a polynomial, 2s to the power 4 minus 5 s square, there is, sorry, s cube, this is s cube. Okay, there is no square term, so I can write 0 into s square, then 5s minus 2, that is equals to 0. Now we can make Routh-Hurwitz criteria, s to the power 4, s cube, s square, s1 and s to the power 0. Okay, we can make this table. So what is this one? First row, this is 2, then this one, that is 0, then the constant term, it is minus 2, then s cube coefficient is minus 5, then s coefficient is 5. Is it okay? Now I have to find out the elements of this row s square. So what I will do, I will multiply this one. So 5 into 0 is 0, and this is minus 2 into 5 is 10 upon this minus 5. Okay, and there is no element, so this 2 is coming here, minus 2 is coming here, so minus 2 will be here. Okay, so what is this term? Can you identify this term? This term is equals to how much? It is simply 2. So this is 2 and minus 2. Now I can simplify this thing. So if the elements are divisible by some numbers, okay, so they are having common multipliers, that we can divide. Okay, so what I can do, I can rewrite it, it will make simple. So this 2, 0, minus 2, here also I can divide by 2. I can make it, this is 1 and this is also minus 1. Okay, and this s cube, there also I will divide by 5, both element, minus 1 and 1. Then I will get s square. So again I will divide by 2, all the elements. This is 1 and minus 1. Is it okay? Is it perfect? Can you reply please? So far it is fine? Okay, can I please reply? Anybody? Can I proceed? Yeah, so then x to the power 1 is how much? This is 1 into 1, 1, this is minus 1 is again 1, so it will give you 0. And last one, this s to the power 0 will be this term, last term, this terms, that is your minus 1. Okay, now as one element is 0, so that is the idea is, already I have said that if this is 0 obviously from above you will get one auxiliary equation. From here we will get one auxiliary equation. That equation is, what is this? This is the A of S, I can write. This is 1 into a square and this is minus 1. Okay, and that I can make it 0, then I can solve it and I will get the solutions. That will be the factor of this one. Meaning is that this is a square minus 1. So these two factors, one is S plus 1 and S minus 1. I have two factors, S plus 1 and S minus 1. These two factors already it is known for this polynomial. So other two factors also we can find out. Okay, so if you divide by this total polynomial by S square minus 1, we will get the rest polynomial, rest factor, and from that we can solve it, we can get the idea. So already you can see that one pole at minus 1 and one pole at right hand side plus 1. Okay, so I need to find out how many number of elements are there. Here actually zeros, so number of zeros on the right hand side. So already I have got 1 0 on right hand side. So from other factors we can find out. So two ways we can solve this problem. Okay, I will show you both the cases. So its answer is 3. So two way means how can I proceed this thing? So one easy way is that already we have got AS auxiliary equation, that is your A square minus 1. So from here you will take derivative of this one. So derivative of AS with respect to S, that you will give you 2 into S. Okay. Now you can see we had these things, S to the power 4, S cube, S square, S1 and S0. Okay. So can you see this one? This is 1 0 minus 1, all our things are there. So 1 0 minus 1, then probably we have got minus 1 and plus 1, is it right? And then 1 minus 1, and then here we got 0, right? So S to the power 1, this element was 0, that we can replace by its power because its power is 1. Now its coefficient will be replaced by here. So first take the derivative of auxiliary equation, then you will get one less power. So earlier if it was a square, so obviously you will get S to the power 1 power, its coefficient should be placed here. Then we will continue and rest one, this is minus 1 is coming here. So your total Routh-Hurwitz table is complete. Now just find out how many sign changes are there. Okay, so you can see from here to here the sign change, because it is positive, it is negative. Here it is positive again, so negative to positive again, and one more sign change. This is positive, no sign change, then positive negative, one more sign change. So we have 3 sign changes, that imply we have 3 roots on right hand side. Here it is 3 zeros on right hand side of S plane. Okay, got the point? This is the easiest one. So first find the auxiliary equation from this one, A square terms. So it is A square minus 1. Take derivative of that one, the coefficient of S to the power 1, that will replace here, and we will continue. And then we will consider the first column. From that only number of sign changes will give you number of zeros on the right hand side. Is it perfect? Is it okay? Can you reply please? Yes? I am waiting for your reply. Okay, good. So this is fine. And other procedure that also you need to understand. What I have said, already said that a square minus 1, this should be a factor. So this polynomial 2s to the power 4 minus 5s plus 5s minus 2, that it should have one factor is this thing, a square minus 1. I need to get another factor. Okay, that you can divide. You can divide this polynomial by square minus 1. So easily you can see that first term should be 2a square to get 2 into s to the power 4. And last term is obviously it should be 1 into minus 1 into 2. Then only I should get minus 2. Now we can adjust these things. What should be this one? No? So as it is s term is coming 5s cube, I think it should be minus 5s, because only this s square minus 5s will give you minus 5s cube. So this is the another factor. Quickly I can get it. So what is the solution for this one? Okay, I think that you can find out. So can we have this kind of solutions? I think 2s plus 1 or minus 1, I think, and here again s minus 2. Is it correct? s minus 1, 2s minus 1 and s minus 2, these are the factors, and that will be equals to 0. So what are the solutions? So solutions are s equals to half and 2. Is it okay? Is it fine? So we have got exactly the exact roots. So from here we have got two roots. One is s equals to 1 and minus 1, and other two roots are here, 2 and half. So what are total roots? Roots are minus 1 one thing, 1, 2 and half. You can see these three roots are on right hand side. So number of roots on right hand side is 3. Easily I can say the answer is 3. Any doubt please? How it could be 2? Okay. Because the answer is becoming 3, because there are 3 sign changes in the first column of the Routh-Hurwitz table. Again, after solving this equation, we will have these 4 solutions. One is minus 1, plus 2 and plus half. So these are the 3 roots on the right hand side. So it is number is 3. Joy, it is fine. Joy Sabra or Sabha. Is it clear to you? Is it fine, everybody? To everybody? Now here we are having 3, because you can see I have 1 0 here at minus 1, other one is plus 1, and other one is plus 2, and one more 0 at half. These are the 3. So if you multiply this, so these factors, so this thing having 2, what are the factors? Total factors I can find out. What is that? S plus 1, S minus 1, 2S minus 1 and S minus 2. Okay. If you multiply these 4, you will get this h of s. There is no confusion at all. Okay, you check this thing. So this video will be there. You will repeat this thing if you have some confusion. Okay, we need to proceed. We should get the next problem because we will be discussing more difficult problems. So if you have any doubt, please let me know. So this is the next problem. It appeared in 2019. Now how to solve this problem? So I'll make this bigger. Just read the problem carefully. Okay, so this one we have given one GS. GS is 1 upon s square plus 3s plus 2, and just k is more than 0, right? And it is said that for positive k, we need to find out positive k for which there are exactly two poles of unity feedback system on the imaginary axis, j omega axis is equal to. Okay, again the same type of questions. I have GS 1 upon s square plus 3s plus 2, and here it is multiplied k upon s, one integrating controller. Okay, k upon s, that is multiplied, and then we need to find out this k value for which the closed loop system is having two poles on j omega axis. Okay, so same idea we can use Routh-Hurwitz criteria. It's not difficult. So what I'll do, and can you solve this thing? I'll wait a little bit. Anybody can try? Here this GS is given as 1 upon s square plus 3s plus 2. So this is characteristic equation is 1 plus k upon s, this is the s, times gs. There is no hs, hs is 1, so that will be equals to 0. Okay, now this will give you 1 plus k upon s into s square plus 3s plus 2, right, and then it is equals to 0. Clear? So then I will get I multiply s into s square plus 3s plus 2 plus k, that will be equals to 0. From here what I will get? This is s cube plus 3s square plus 2s plus k, that is equals to 0. Okay, so this is the polynomial. Then from this polynomial we can make Routh-Hurwitz table. So s cube, s square, s to the power 1 and s to the power 0. Okay, now s cube, this coefficient is 1 and s coefficient is 2, then it is s square coefficient is 3 and constant value is k. Sorry, I think it's fine. Is it okay? Please reply, then I will get to know that okay, you are following me. Please reply quickly. After this it is fine. Okay, good. So what I'll do, the next one, this is 3 into 2 is 6 and this k into 1 is k and upon 3 and next one is it is k. The same procedure we will do. I have said that try to equate this h to the power coefficient and this one should be equals to 0. If this is equals to 0, then you will get one auxiliary equation above 1, 3s square plus k equals to 0. Then the poles should be on imaginary axis, critically condition. Okay, so from here what we will get, this 6 minus k will be equals to 0 because 3 by divided by 3 that I can multiply right side, or k equals to 6. So this is the answer. For k equal to 6, you will have two poles on imaginary axis, here and here. And if question was that what is the location for this one, what is the frequency, it is a j omega, fine. So what is the omega, how to find out this one? So from this one we can find out 3 square plus k, that will be equals to 0 and we can replace k value, k already have got, 3 square plus 6 equals to 0. Now 3 I can divide, okay, so a square plus 2 equals to 0. Third solution, is equals to plus minus j square root 2. Okay, so this omega is nothing but, this is the omega, omega is square root 2. But this is not the question. The question was only to find out the k value for which the two poles will be on imaginary axis. So for that what we will do, h to the power 1, that coefficient I will make it 0. Is it fine? Can you reply please? The third problem is okay with you? Okay, good. So we can move to the next one. So this answer we have got it. Okay, the answer is 6. That is perfect. Now problem number 4. It appeared in 2012. Now look at the problem carefully. So one feedback system is given, k times s plus 1 upon s cube plus a square plus 2s plus 1. There is one unity gain feedback is there. Okay. Now we need to find out the k value and a value. For that, the feedback system shown below oscillates at 2 radian per second. Okay, are you getting this problem? So this system will have one oscillation at the output ys. It will oscillate at the frequency 2 radian per second, means omega equal to 2 radian per second. So omega is given. Now we need to find out the k value and a value. It's a little bit critical. So can you solve this problem? So what approach you will take? Again similar kind of approach, means you should have the roots on imaginary axis, perfectly on imaginary axis, then only it will oscillate. That is the meaning. So and this is third order system, So one root will be on left hand side, that is fine, but other two roots should have conjugate roots, and that frequency will be 2, means s equals to plus j2 and minus j2. Okay, in other words, s square plus 4 equals to 0, s square plus 4 equal to 0, that should be a factor for this one. Okay, now let me discuss this thing in detailed way, and its answer would be the first one. Okay, let me solve this problem. Okay, so directly we will go for 1 plus GSHS equals to 0. Okay, so what we will get? Simply 1 plus GS equals to 0. That will give you, so I will multiply this thing, okay, directly. The polynomial will get SQ plus A square plus 2S plus 1. Then I will add this thing, K into S plus 1. That will be equals to 0. I think you can understand. Whenever I will add this one, numerator will be added here. It is coming here, and then denominator, and numerator is here. So numerator plus denominator will give you total 1 plus GSHS, and that is equals to 0. Okay, and this one little bit I can simplify. This is the SQ coefficient, only 1, and 1 S square coefficient is fine, but S coefficient is 2 times is there. Here it is 2, and here it is K. Okay, if I make any mistake, please let me know. Then this is 1 plus K, and that is equals to 0. Okay, now can we make Routh-Hurwitz table? Okay, SQ, A square, S to the power 1, S to the power 0. Okay, SQ coefficient is 1. This coefficient is 2 plus K, and then S square coefficient, this one is A, and this one is 1 plus K. In that way we can do, right? And last term, this term will be the 1 plus K. Right? Now in this case you have now am I visible? Okay, is it fine? So what is the coefficient of the S to the power 1? This is this one, A into 2 plus K minus 1 plus K, and it's upon A. Is it fine? So that I want to make it 0. I should make it 0. Then only I will get these things. But here is one problem if we use this kind of methods. So that I can make it 0. So from here, what equation I will get? A times 2 plus K minus 1 plus K, and that is equals to 0. Right? And so this is one equation you will get. The A will be simply 1 plus K upon 2 plus K. That's okay. But from above you will get one auxiliary equation. A square plus 1 plus k, that will be equals to 0. This is the auxiliary equation. And if you solve this one, if I put s equals to j2, it should work, right? So I will get another one, this thing. So already it is said that s square, because a is equals to plus j2 and minus j2. This is oscillation. The omega is 2, thus basically s equal to j omega. So what is happening? S square equal to minus 4. Okay, that I can replace here. I can replace s square equal to minus 4 here. It is a little bit difficult. So it is minus 4 times a plus 1 plus k, that is equals to 0. Right? Okay. Now this equation and this equation, can you solve? Can you find a and k? Anybody? Is it fine? Everything? Can you solve these things? Can you find a and k? I think it was is there, no? It was is there. Anyway. Anybody can solve it. It is very easy. Just so 1 plus, I can replace a by the a there. So 1 plus k or 1 plus k, I can replace a into 2 plus k. So I can go for 1 minute. So what is this? This thing we have got it. Perfect. Okay, so this, from these two equations, we need to solve it. How to solve it? So I can replace from here. So minus 4 a can replace 1 plus k upon 2 plus k plus 1 plus k equals to 0. So 1 plus k I can take common. Okay. So from here I will get minus 4 and then I will make it 0. And but k cannot be negative, remember. So I can divide by 1 plus k. It is 2 plus k plus 1 equals to 0. And that implies this 4 upon 2 plus k equals to 1, and that is 4 equals to 2 plus k, and that implies k equals to 2. Is it okay? And once we will get k equal to, what is a? 1 plus 2 upon 2 plus 2. So I replace k here. So it is 3 by 4 means 0.75. So a value is 0.75 and k is 2. Any doubt, please let me know. This is one critical problem. We can use Routh-Hurwitz criteria and we can solve these things. So this is one way. Another way is that, so in this above equation only, in this equation we can replace s equals to plus minus j2. Then we will equate this real term equals to 0 and imaginary term also equals to 0. Eventually you will get the same result. Okay, that also you can do. Any doubt, please let me know. Otherwise, we'll go to the next problem. Is it fine to everybody? How to solve this kind of problem? This problem appeared in 2012. It's a nice problem. Two unknown things, one is capital K, other one is small a. These two we need to find out, not only one parameter, two parameters. It's okay? Please reply. We can go to the next level. Yes, it's fine. I am not getting a response. So if this is clear, then only we will go to the next few problems I can discuss. Those are also critical. Fine. I think it's yes. So can you solve this problem then? So this is 2021 gate problem. Just go through this problem carefully and try to solve it. It's again one difficult problem. So I have one system. This is the system here. 2 upon s cube plus 4 square plus 5s plus 2. And we have one PI controller, Kp plus Ki upon s. This is your PI controller. This is your system. Now here we need to tune these two parameters Kp and Ki. Okay. The stability of the overall system is controlled by tuning PI controller parameters Kp and Ki. The maximum value of Ki that can be chosen so as to keep overall system stable. In the worst case, marginally stable. Okay. So can you solve this problem? I think really it is a challenging problem. Can you try to solve it? So we need to find out maximum value for Ki. So nothing is given for Kp. Okay, Kp is not asked. So only thing is that maximum value of Ki that we can choose, still will have stable system. Means we can go up to marginal stability. So we want to use Routh-Hurwitz criteria. Right? So what I'll do, okay, let me consider this one. The system. So what the equation? Equation is Kp plus Ki upon s times 2 times s cube plus 4 square plus 5s plus 2. And then I need to add plus 1 plus GSHS, and that should be equals to 0. Okay. So if I simplify it a little bit, what I will get? So this is your 2 times Ki plus Kp times As, and this one is becoming S into this factor Sq plus 4 square plus 5S plus 2 plus 1 equals to 0. So what is your characteristic equation? So this product I can write in this form: S to the power 4 plus 4 Sq plus 5 square plus 2S, this denominator that I have written, okay, plus the numerator 2 Ki plus 2 Kp into S, and that will be equals to 0. Okay, so this last one we can work on. So this one, so, and its answer, it's saying that 3.1225. Okay, so what is your polynomial that I can give here? Now can you find Routh-Hurwitz table? Okay, S4, SQ, S square, S to the power 1, S to the power 0. Okay, so what is the S4 coefficient? This is 1, this one is 5, and S constant term is 2 Ki, right? And SQ, this is 4, and S term, this together, remember 2 plus 2 Kp, or I can write 2 into 1 plus Kp. I think it is fine. So what is the second term, third term, and for all those things we need to find out. So this one. So here one thing I can do, I can simplify this thing, I can divide by 2. That I can do, right? I can divide this thing by 2. So this 2 to 4 and 2 is 1. All elements I can divide by same factors, that is permissible. So this is 2 and 1. So what is happening? The next element, this one. So 2 into 5 is 10, and this is your minus 1 minus Kp by 2. Am I correct? And this is 2 Ki is coming. Next one is 2 Ki. So what is happening? This term is 9 minus Kp, and then next one will be this product multiplication. So this is suppose x, okay, that I am writing here. What is the x? X equals to this product. So this is your 9 minus Kp. So 9 minus Kp by 2 times 1 plus Kp, okay, minus this one, 2 into 2 Ki means 4 Ki, and it's divided by that factors. This one, 9 minus Kp by 2. So this is your x, and last term will be 2 Ki. Okay. Now for stability, what is the required thing? Required thing is that all elements should be positive, and for marginal stability I have said that one part we can make it 0. Okay, that we can go for ultimate at the towards the worst cases. Okay, but not always necessary. Okay, but in this case, so for marginal stability, what is the requirement? X should be equals to 0, right? And this this element is becoming 9 minus kp. 9, so this one condition is that this 9 minus kp should be positive. That imply kp should be less than 9. Okay, and next one, this one I will put it equal to 0. Okay, because then only it will be marginally stable. I think you are getting the point. If this is becoming 0, we will get auxiliary equation above. Are you getting this one? Am I fine to everybody? Any confusion? Please think carefully. This is more critical problem. It's not easy problem to solve it. So every element should be positive. So a squared, these terms I have considered first. 9 minus kp is more than 0. So kp should be less than 9. Then for marginal stability, this part should be 0. Means this part should be 0. So what I will get? So 2 into 4, 8 ki. Can I write this thing? 8 ki equals to 9 minus kp, and it is your 1 plus kp. Okay, this is required condition for marginal stability. Are you convinced? Can you reply please? Can you reply please? Good. So this is a condition. Now what I will do? I need to find out maximum value of ki. Okay. Now we will use our mathematics. So this is the required condition. So I will go for this thing. I will remove. Okay. 1 minute please. Okay, so this part I need to maximize, and already we have said that this kp should be less than 9. That I have got it. Now we need to maximize ki. So what I will do? So 8 is fine. I can divide. So this term, the dki dkp, that should be equal to 0 for maximization problem, because anything below this kp less than 9, it is fine for us. Now I want to maximize this thing, this ki value, so I will take derivative. So 8 times of that is fine for me. So how to take the derivative? So this one is constant, 9 minus kp, and derivative of second term will be 1 plus, now 1 plus kp is constant, and derivative of 9 minus kp will be minus 1, and that is equals to 0. Okay, so what is solution? 9 minus kp plus 1 or minus 1. It's a minus 1. Okay. And it is minus Kp. Any two factors all are there? Probably I have not considered. So is it fine or any mistake? So answers a little bit. I think Kp we are making somewhere problems. So anyway, so this is the approach that you can see. So it is your 8 minus 2 Kp equals to 0. So what is the Kp value? Kp is your 4. Okay. So any doubt about these things? Is it fine to everybody? So if you replace this Kp equal to 4, what is the Ki? Now from here you can find out the maximum value for Ki. Right? So the Ki value I write here, okay? The Ki is your 9 minus Kp and 1 plus Kp upon 8. So can you simplify please? So this Kp is 4. So this is your 9 minus 4 is 5. 4 plus 1 is 5 upon 8. So it's 25 by 8. Meaning is that 3.125. Okay, it's fine. So answer is perfect. So answer is given as 3.125. So you can see the difficulty level. It's a great problem. Hope you have understood. So two things you need to keep in mind, that we have to use Routh-Hurwitz table, and for marginal stability ST for 1 I will make it 0. From that I will use get one equation, and we will get some condition on other parts. From the first row every element should be positive, okay, then only system will be stable. So that we have done, we have got the equations and Kp we have got. Now we will maximize Ki. So dKi dKp I will do these things. For what value of Kp the Ki is maximum, that I have done. Okay, I think it is a little bit tricky, and if you have any doubt please you will go through it again. So this video will be recorded. Okay, next problem. Can you solve this one? I'll make it bigger one. I think you can do these things by yourself. So one plant transfer function is given. Again it is total product is given, Kp plus Ki upon S times 1 upon S into S plus 2, means PI controller as well as the system, the product is already given. Now unit gain feedback is provided. Now you need to find out the condition for stability. So which one is true? Can you do this thing? Can you try quickly? Okay. So okay, let me do these things quickly. So what is the GS? HS 1 plus GS should be equals to 0. So 1 plus Kp plus Ki upon S into 1 upon S into S plus 2, that should be equals to 0. Okay. So if I multiply all the things, what I will get? 1 plus, this is your Kp into S plus Ki upon S into S square, it is S plus 2, that is equals to 0. So if you simplify it, this will be your SQ plus 2S square plus Kp into S plus Ki, that is equals to 0. Right? Now it's very simple. Can you solve this problem? Can you make Routh-Hurwitz table? SQ, S square, S1, S2 to the power 0. It's very easy problem right now. So SQ coefficient is 1 and S coefficient is Kp. S square coefficient is 2 and constant term is Ki. So what is the next term? Next term is 2 Kp, this product, minus Ki, this by 2, and last one is Ki. Is it okay? So what is the condition for stability? Every element should be positive. So this one should be positive. So Ki should be positive. And this one should be also positive. And for this one, what you will get? 2 Kp minus Ki, it should be positive. In other words, Kp should be more than Ki by 2. Okay. So can I write then, and they already said that Ki is more than 0. So can I say that it is more than 0? So this will be the required condition. Kp is more than Ki by 2 and that is more than 0. Yes, C is also correct, partially correct. 2 Ki is less than Kp, but it is nothing said whether Ki is more than 0. Okay, so you need to include that also. Have you got these things? So C is not perfect because it is not said about their own values. It could be negative or not. So already we have seen that Ki should be positive, that we should make sure. Okay, so thus answer A will be the perfect one. Is it fine to everybody? Yes, good. So I think you have got it. This is perfect. Now just quickly, so this answer is A. Now can you solve this problem quickly? And I want some answer from you. Can you solve it? A forward path transfer function of unity negative feedback system is given. Gs equals to K upon S plus 2 into S minus 1. The value of K for which both the poles of closed loop system at the same location is. Yes, please do it and solve this problem so that you have learned from these lectures. So okay, everybody can try, please. Can you solve this thing? So note that the requirement is that both the poles should be at the same location. That you can make certain concentration on that, okay? It's a very, very simple problem. Nothing is required. No need to use Routh-Hurwitz anything. Very simple problem. K equal to 2. Is it the answer? Any other? Anybody tried for that? Answer shows 2.25. Not exactly 2, it is 2.25. Are you making mistake somewhere? So let us see. It's very simple problem. We can solve it within a minute. So 1 plus gs, that will be equals to 0. That means 1 plus k upon s plus 2 times s minus 1, that is equals to 0. Right? So what you will get? This is your this product, s square plus s minus 2 plus k, this is 0. So it is saying that it should have the same location, means square form. Something, so this should be of this form, s plus alpha, that square, that will be equal to 0. Then solution will be s equals to minus alpha and again minus alpha. Can I make it square? That is the required condition. So you can see here it's a square, 2 into s, so it should be equal to half to make it 1. So this part, this is your k minus 2, no? So you can see that it will be equals to s plus half, that whole square equals to 0. So if k minus 2 equals to 1 by 2 square, so what is the requirement? This k minus 2 should be equals to 1/4, half square. In other words, k equals to 2 plus 1 by 4 means 2.25. Good. What you have done? See, it's simply that you have to make a square, then only you will get the same pole at the same locations. It is 2.25 for this k value. And what is the location? S equals to minus half. That also we can find out. But that is not the question. But the question is that what is the location? That will be s equals to minus half. Okay. Is it fine? Okay. Now, so this is the okay. I think you can try. This is the question I am giving to all of you. You will solve it and you will share in the comment section. Just note this problem. So one open loop system is given. This output is omega s, input is your rs, but the system function is given 10 upon 1 plus 10s. Now question is this one, that now we will have one proportional idea Ka multiplied, and because of this Ka, with this negative feedback, what is happening? It will reduce the time constant of the closed loop system. Okay. Then it says that it will reduce the time constant of the closed systems by 100 times. So by 100 times it is reduced. Then we need to find out the value for K. For what value for K, the time constant is reduced by 100 times in closed loop system. So you can solve this problem, and you can share your answer here. Is it okay? Now, have you got certain idea from this lecture? Is it useful to everybody? Those who are currently watching this video, is this video useful to all of you? I think we are going to end this lecture today because it is more than 1.5 hours. And you solve this problem, and please share your answer in the comment section. Okay. So this kind of problem could be asked in any exam paper. So I have collected all the gate problems. You can collect some other gate problems. We can solve this kind of problems in a regular way in every week. That I will try my best. So try to attend the lectures. You will learn lots of things. Okay. So thanks for watching. Thank you. Thank you very much. We are going to end this session. Okay. Thanks a lot.